Hello again, welcome back. So our next topic is looking at games with incomplete information. So what does that mean? That means that players might have some uncertainty about the payoffs, about what other players might be doing, about the general structure of the game. And this is one of the most interesting and powerful areas of game theory. And just to give you an idea of some of the applications that it covers, if you want to model bidding in auctions, generally a bidder might have some information about their own value. They might even have incomplete information about their own value. So if I'm bidding in an auction for treasury bonds, for instance, I have to forecast what the value of those bonds are going to be, how many other bidders there might be, how aggressive the other bidders are going to be. If I'm thinking about regulating an industry, for suppose you wanted to think about regulating investment banks, how should you structure the regulations in order to make sure that banks take decisions that you'd like to see them taking as a regulator, given that they're going to have information about the value of different securities. In political science, how should a political candidate campaign? So if they're not quite sure of what other candidates are going to do or what the populace's views are over certain things, what decisions should they make? What prices should a firm charge? How does that depend on the distribution of consumers' values? How does that depend on what competitors might do? If you're structuring incentives to try and get workers to perform for you, how do you structure those incentives given that workers are not always being monitored and you can't tell exactly what they're doing or what they know at any particular time? So all of these involve some incomplete information, and game theory has become a very powerful tool for analyzing these. And as such, there's been a very large growth in the use of incomplete information games for understanding a whole series of economic and social interactions. So let's have a look at this. So in terms of the structure of our analysis here, what we'll do is start with just a simple example to give you some motivation and understanding of the basic ideas. Then we'll go through some formal definitions, and then we'll come back to some applications. Okay, so let's start with a simple example. And this is an example which is a game of conflict, similar to some of the hawk-dove games or other games that we've talked about a little bit before. And what's different about this game is that player one could come in two different forms, either a strong player or a weak player. So let's look at a situation where player one could be strong or weak. So player one is the role player here. And depending on whether they're strong or weak, the payoffs from different combinations of actions change. So here we have each player has a choice of either having a conflict with the other player or not. So they can either fight or not fight. And we can think of this as two companies, one suing another, or we could think of it as conflict, war possibly between two countries. We could think of it as a whole series of different conflictual situations. And in particular, if they both fight, then the outcome depends on whether player one is strong or weak. So we can think of a situation where if player one is strong, then if they both end up fighting, then player one gets a payoff of 1, and player 2 loses, gets a payoff of -2. So this is costly for player 2. If player 1 is strong, player 1 is going to end up winning the fight. If player 2 chooses not to fight, that's actually better for player 1. They don't have to expend as much energy. They would end up with a higher payoff. And also it's better for player 2. So in a situation where you're facing a strong opponent, not fighting would be the better strategy for player 2. What's different is if they're playing a weak opponent, then if they don't fight and give in, they get the same payoffs as if they were playing a strong, so they give up. The player 1 walks off winning, player 2 ends up losing. If they fight, instead it's player 2 that wins. So when playing a weak opponent, it's player 2 that wins. And the payoffs here are symmetric in the sense that if player 1 ends up not fighting against player 2, then player 2 ends up winning and player 1 ends up losing. And in the situations where neither ends up fighting, then they just have a status quo of 0-0. Okay, so let's first, just as a benchmark, see what the players would do if they were always able to tell what player one's type was. So that if both players knew whether player one was strong or weak. So when we look at player one being strong, player one here has a strictly dominant strategy of fighting. So for the strong player, so if they're strong, they get 1 from fighting if the other player fights, -1 from not fighting. They get 2 if the other player doesn't fight, and 0 if they don't. So in each case, they're strictly better off fighting. So if player 1 is a strong player, they should fight for sure. Okay. So if they're fighting for sure, now player 2 is faced with either a -2 or a -1. So in this case, they should not fight. They get a better payoff from not fighting, given that player 1 is strong. It's a strictly dominant strategy for them to fight. That's regardless, any best response has to be for them to fight. The only possible equilibrium here is for player 2 not to fight and player 1 to fight. Okay, now let's go to the weak situation. So if player 1 is weak, well, then if we look at the situation from player 2's perspective, now it becomes a strictly dominant strategy for player 2 to fight, right? So they're getting a higher payoff here and here. So player 2 should fight no matter what. And given that player 2 should be fighting, then player 1's best response is not to fight. So we end up with a situation where if player 1 is weak, then player 2 should fight and player 1 should not. Okay, so what does that tell us? That tells us we have unique pure strategy equilibria in these games if we're in a situation where everybody sees exactly what's going on. So in the case where it's strong, then we end up here with player 1 fighting, player 2 giving up. And if player 1 is weak, then we end up with just the opposite. Okay, so a fairly simple, straightforward game to analyze with a very obvious conclusion. Okay, so now let's look at where the game gets interesting. What happens if player 1 is the only person who knows whether they're strong or weak? So now we have a probability P that player 1 is strong, a probability 1 minus P that player 1 is weak. And player 1 gets to see whether they're strong or weak, so they know how strong they are, but player 2 can only guess. And in particular, all they see is P or 1 minus P as probabilities, and then they have to guess what's going to happen. Okay, so now specifying an equilibrium is a little more complicated. What do we have to do? In this structure now, an equilibrium is going to be a specification of what every player does given their information and best responding against what every other player is doing given their information. So we'll have to have a specification of strategies. So what is, in this case, what does player 1 do when they're strong? What does player 1 do when they're weak? And then what does player 2 do given that they don't know anything? And we want to make choices here such that each player is maximizing the payoff given the other player's strategy. We'll come back and give more formal definitions, but this will get us through this example. So we just need to specify what player 1 does in each case, and then player 2, what they do, just given that they only know that there's a probability P of being in this situation and a probability 1 minus P of being in this situation. Okay, so let's just look for an equilibrium. And in particular, we can start by just looking for a particular type of equilibrium, and we'll come back to look for more later. So let's see if we can find an equilibrium of the following form. The strong type of player 1 is always going to have a dominant strategy to fight, right? So if player 1 is strong, they should fight no matter what. So let's look for a strategy where player 1 fights when they're strong. And now in terms of the more interesting part is whether they fight or not when they're weak. And whether they choose to fight is going to depend on whether they think the other player is not going to fight or fight, right? So if they think player 2 is not going to fight, then they'd be better off fighting. If they think player 2 is going to fight, then they'd be better off not. So let's look for a situation where they fight, and then where player 2 is not going to fight. Okay, so let's see if we can find a situation where player 1 now always fights and player 2 does not fight. Okay, well, what has to be true for player 2 in order to not fight in these situations? Well, if player 1 is always fighting, we can write down what's the expected payoff to player 2 if they fight, and what's the expected payoff to player 2 if they don't fight. So if player 1 is following the strategy of always fighting, player 2 chooses not to fight, what's going to happen? Well, if they choose not to fight, they get a -1 no matter what. So the uncertainty doesn't matter. No matter what happens, they get a -1 if they choose not to fight and the other player's fighting. If they choose to fight instead, then what's going to happen? Well, with probability P, they're going to be facing the strong opponent, and they're going to get a -2. So that's this part down here. And with a probability 1 minus P, they're facing the weak opponent, and they'll actually end up winning the fight, and they'll get the 1 here. So that's a 1 minus P times 1. So their payoff from fighting is this expression here, P times -2 plus 1 minus P times 1. And which of these is bigger, whether they're better to fight or not to fight, is going to depend on how large P is. The larger P is, the more attractive not fighting is going to become, and the smaller P is, the more attractive fighting becomes. Okay, so let's have a look then. So if we want to see the situation where these are exactly equal to each other, so if you set this equal to this, when is player 2 exactly indifferent between fighting and not, you can solve that equation there. So P times, so -2P plus 1 minus P equals -1. Solve that. What do you get? You get P is equal to 2/3. So this strategy, fight, gives a better payoff if P is lower. So you've got more weight on the weak player. And in situations where P is high, above 2/3, then you're better off not fighting. Okay. So player 2's best response here depends on what this probability is, depends on the uncertainty, and the equilibrium then is going to depend on what the structure of the random choice of nature, in this case of whether player 1 is strong or weak, is. Okay, so in this situation then where P is bigger than 2/3, what do we end up with? We ended up with an equilibrium. In that situation, we can have player 1 fight no matter what. They fight when they're weak, they fight when they're strong. Player 2 chooses not to fight. So, and what happens? They end up getting a payoff of -1 no matter what. But if they chose to fight instead, well, they would end up with more than a 2/3 chance of getting the -2, less than a 1/3 chance of getting the 1. So they're better off just settling for the -1, not fighting. And so we end up with a different structure than what we ended up with in the complete information game. So here player 2 is at somewhat of a disadvantage from not knowing what's going on. What we end up with is player 1's weak type benefits from player 2's uncertainty. And now we have a different equilibrium where the equilibrium is basically player 1 always fights and player 2 gives up, does not fight. And the fact that there's a strong probability, a large probability that player 2 is facing a strong opponent means that this is the best thing that player 2 can actually do in response to player 1 always fighting. So we end up with an equilibrium which is different in the incomplete information setting than what we saw in the complete information setting. So now what we need is a framework for generally specifying these kinds of equilibria, understanding how to analyze these, and seeing what they imply for different kinds of applications.